Right. Yeah, about time. I'm actually here slightly early today. So Favonia and I have been out of town. You guys got a week's vacation. I hope you didn't lose all of the context that we built up since the first 2 weeks of lectures. I got a lot of feedback, I will say, about the last lecture, so which I think I made some assumptions that were not necessarily valid for most people, so I want to make sure I want to step back and just catch a few. I put out a Piazza post, but I want to step back and remind us where we are, and then we're going to move forward. So as we've had before, which I won't repeat, we first of all talked about logic via provability, and that is the condition of truth constructively, which is this is our notion of truth. For the purposes of constructive logic, means that you have a proof, and then we develop the idea that we have a consequence relation, which in the logical tradition is usually written like that, saying that this is A is a consequence of A1 through AN, and then we related that to an order theoretic interpretation, which is you take the mean of all of these things and say that they're less than A. So these are sort of considered analogous to one another, and in your homework we developed an exact correspondence. So this was in what are called Heyting algebras, as we talked about it, and this was in I called it, I think, intuitionistic propositional logic, that we wrote like that. So we first of all developed that, and that's like a very standard way of treating logic, is to focus on what is true and to focus on, for example, an order theoretic interpretations like this. In order to address the idea of things being, what is the characteristics of intuitionistic propositional logic and how those relate to classical reasoning, and moreover how they relate to Boolean algebras, I use that as a jumping off point to talk about the logic of proofs. And so I wanted to actually examine the structure of proofs. So what we did is the first thing that we could do is we could introduce a notation for proofs. So you can think of it as kind of instrumenting logic, okay, with some what are called proof terms, as we know. So this is M is a proof of A, and you have a bunch of variables representing the names, if you will, of the assumptions that we're reasoning from, or in other words, they vary over the possible proofs of each of these assumptions. So that was which was our logic of proof terms, and this inevitably, I claim, but I will well, let me take back the word inevitably, but then I broached the subject of identity of proofs. So we also looked at what it would mean for two proofs to be equal. And so one notation for that would be M is equal to N and A, written with usually a common notation for that is a triple bar. And we were looking at what might be principles for defining when two proofs are equal. So think of this as being, so the intuition that I'm trying to convey is that as soon as you bring up the idea of there being some object like a proof term, it's natural to ask the question, when are they equal? When are two of them equal? How do you know you're looking at one, and when are they the same? So so what I wanted to do is get us into a position so that we could realize that there's an interesting question there. I'm basically teaching everything from the assumption that you don't already know type theory. So so you want to ask the question, you want to broach the right sort of questions, and I want to get us to the position so that we can see that there's some interesting issues already as soon as we start to look at that. So one way we did this, which I'm, you've got the message here from Favonia. I'll erase it. So one way in which we did this is we applied the proof theoretic principles. So we had Genson's inversion principles, which I will briefly summarize as the beta rules. I'll write beta like that. And without repeating everything, I don't want to write everything down that we did last time. Without repeating everything, the critical ones were these, that if I just write them like this, if I take first of a pair, then that should be equal to m, and second of a pair should be equal to n. And if you recall, the notation was, this is the introductory form for conjunction, this is the eliminatory form, and they cancel. So that was that, and then the other form of cancellation, another form of cancellation we had is the introductory form for implication is a lambda, and the eliminatory form is application. And so this is written like that. So we do substitution, and I left it as an aside that you should go look up the definition of substitution, so I don't spend a lot of time explaining those details. They're actually intricate and tricky if you don't know them, but I don't want to go into them here. So this is these are the beta principles. So this is for cross. Oops, sorry. Before I get that notation, this is for conjunction and this is for implication. And then for disjunction, we had, I don't remember the notation I used. It might have been case. So we had something like case of in left of m. It gets a little heavy to write out, but can't avoid that. And we write down, it would be m for xp. So we do a case analysis, and we do a case analysis on in right of m x dot p y dot q, and this would be m for yq. So this was the beta rule for disjunction, like that. Okay, so we had, these are called the beta principles. So as I was saying, is Gensen's idea was a kind of, you could look at this as a proof simplification, which it is, of course, at least for some notion of simplifying. So I've at least gotten rid of a redex here, that I've gotten rid of a scenario of an introduction followed immediately by elimination, but this is typically a, so to say, a physically larger term than this one, so you have to ask, what does it mean to simplify? But in a certain way, I'm simplifying, okay, these terms, and that can be made precise, but that's the idea. So he gave these rules for simplification, and we interpreted these as giving a dynamics of proof. You could look at it like that, meaning that proofs are programs. Okay, at this point, I have so little developed at the moment that it would be hard to see what interesting program you could write in such a little language. So I'm really asking you to, suspend disbelief, because other things will then, be accreted onto this basic framework, and then it will be more interesting. But anyway, whether it's an interesting programming language for the time being, let's just suspend that. But it's a notion of proofs being programs that I can run them. In fact, the natural thing is to think of these as oriented from left to right, and then I can kind of run them by this process of simplification. Or at any rate, it's a notion of computation by calculation, by just doing some formal manipulations. So that was one of Gensen's great ideas. And then so that was some principle of proof. And in fact, I give these a name. These are generally following Church called beta rules. And then Gensen also considered unicity principles, which I will call eta rules. And that's just following Church's notational convention. So, and by now extremely standard. So the eta principles are expressing some kind of other notion of equivalence of proof, and that was what I was trying to broach with you. And the thing is that in order to state them, I need already more information. So you'll notice is that I was able to express the beta principles without really mentioning anything about types. I didn't really need to worry about being extremely careful. Officially, right, this is the judgment for this notion of equality, and officially I should write these down with some context and what their types is, but to express the beta rules, you don't really need to do that. For the eta rules, you do. So there's already something different going on. So an example of this, and now I must write it in the official form in order for it to make any sense at all. And I even have to write it as a rule rather than one equation. And the rule would be this. It says, if you have any proof of truth, it's tantamount to, for lack of a better way of formulating it, the trivial loop, the trivial proof of truth. Okay, that it's equivalent to, the notation we wrote is the null tuple, just the way of ticking off that the trivially true proposition is true. So that was our grammar for that. But notice that I need to state this. If I erase the surrounding context here and just wrote m equals null tuple, then the theory is inconsistent because everything is equal to everything else, right? Going via this guy, because given m and n, m is this and n is this, and therefore m is n, because we're talking about an equivalence relation. And so obviously I cannot just state this. I mean, I can use Blackboard conventions and say, oh, you know, but I want to be careful about what I'm assuming here. So to be careful, I have to put in the type information, and then it makes sense as an equation. Without the type information, they don't make sense. So that's a first little sign that something is different. And there was a similar thing which was written in the traditional formulation. It's written like this. We talked about it, first of m. If I take the pair first m, second m, or in fact, let me even write this. It'll be a little, just for the sake of the symmetry, let me write it out just to throw it into your eye. If you give me any term, any proof of a conjunction, then that proof can be put into standard form, where standard form means it's a pair. And the way you do that is kind of in the trivial way. You say it's first of m, and you say second of m. Okay, is A and B. And in fact, if you think about it for a moment, you can really see then this is the degenerate form of that, because if truth is the zero-ary conjunction, then this is the null tuple as opposed to the binary tuple. So in a way, those are expressing the same idea. Okay, so this is the notion of conjunction. And what I was pointing out to you using the diagrammatic notation is you can put this into a slightly different form, which I'll write over here, that may be helpful to see, which is to say that we have the following idea, that if I have some arbitrary term m of A and B, okay, such that, okay, and then this is what we did last time, so we then know that first of m is, let's call it P, and we know that second of m is Q. I'm really saying the same thing in a different way. I'm just doing it for a reason too, and I really should put in this would be A and this would be B. Then that m can be none other than the pair and PQ. Okay. And these two formulations are the same. There's no difference. All I did was, assuming that I'm dealing with a congruence, I didn't write down all the rules, but that you can replace equals by equals everywhere. So you just take, P and replace it by first of m, and take Q and replace it by second of m, and you'll get the equation that you had over here. And conversely, if you have the beta rules around, then you can just take this to be the term in question and calculate, and you'll get the same kind of result. So this was another way of saying the exact same thing, but this is kind of the classical way of saying it. This is the usual way of saying it. And then there's a rule, and again there's a usual way of saying it. It says if you give me anything which is an implication, then I can put that implication in standard form by forming lambda x mx of A applied to B, where, if you like to write it like that or something, it's inside there, where x is chosen so that x is not it's not declared in gamma. So in other words, it's a variable, a fresh variable. And again, taken by itself, you just say, oh yeah, okay, that makes sense, right? The function m is the same as the function that when you call it calls m. That is the little handoff is not significant. These two proofs are this. You can say those two proofs are the same. And similarly, although a little bit more awkwardly, this can be expressed in a way that looks like that. I'll skip that for a second. And I wanted to get to the rules of disjunction. Because the rules of disjunction, which is what I didn't get to last time, is where it becomes more important to think in this way. So in order to express that, let me remind you, because this is the part that I think threw a lot of people, judging from talking to a few people in the corridor and email. So let's put this in the situation. Now let's look at the situation with products again in diagrammatic form. So the idea is that, so we're going to focus on the conjunction here. So here we have conjunction, here's truth, here's implication. And we kind of got all sort of bollocksed up, and I wanted to put things in diagrammatic form. In order to do that, I want to mention that there's another notation that one uses, which is similar to the analogy that I have here. So the analogy here, this thing is analogous to, by a very similar pattern of reasoning, to the notion of a map in a category, which I can write like this, which we then write A1 cross AN, or in fact I could also write it and, but I'm going to develop the typical notation is cross and arrow written like that A. And the analogous thing is that, so I have an arrow in what is called, so this is in what is called eventually it will be called a bi-CCC. It's a bi-Cartesian closed category. And we can have this notion of two things being equal as maps in a bi-CCC. So I'm trying to draw a correspondence. This correspondence is that correspondence. That's what I'm trying to get at here. So these two things go together. And I haven't formally said what is a bi-CCC, and I haven't formally said what I mean by that. Okay, which is what I'm about to do, okay, now, and I'm just going to remind you, we did this last time. So this part of things, people found confusing because they weren't familiar with it. So this is what I want to mention very carefully. So the idea is, if you look at the analogy that's going here, you notice that we took the meat of all of the things on the left. This is a technical convenience, I guess is the best way I could say it, is that there's some structure in these Heyting algebras that lets me take n things and smush them together and make them one. And you do that with the meat, and the meat expresses this. And we asked you to look at in homework that indeed this correspondence makes sense. So there's a similar thing here, is that I'm smushing everything together. I have n assumptions, and I'm really turning this into one assumption. So you can kind of say that the first thing is basically the same as, you could think of it as an intermediate step in which I have one variable that has a conjunction as its type, and then oops, I'm sorry if I'm going to use the proof term notation, then it would be M is A. So that would be what would be corresponding here. And there's a little move here, which is that you keep everything in conjoined form. It introduces some bookkeeping overhead, but it simplifies the discussion about how you relate this to that. That's the reason why you do it. And I got a little discombobulated because the problem is there's an order of presentation. In order to explain this story, I first have to tell you what cross is. And in order to tell you that story, I wanted to at least use the ideas of logic. So there was conjunction and product. It's a little awkward to explain that. So that's what's happening here. So modulo notation, if you want, you're perfectly free to write this as a conjunction if it helps to remind you that that's what we want. It's not the conventional notation, but but there's no reason why you can't do that. So you could write it in that way. Okay, so that meant that's not a hat. That meant you can do this either or. You could write these either way, whichever seems nicer to you. Okay, in order to guide the analogies. So from the point of view of proof term, you can always say there's only one lemma in the world. It's just a big conjunction. That's all it's saying. That's all we're saying. It's trivial. It has to do with just the technicalities of developing everything. Okay, so that's the analogy I wanted to develop. So this formulation of the rule then can be expressed now diagrammatically once I have this notation that I had over here in the following way. Well, It's traditional to write it as cross, so I'll write it as cross, okay? Which says that when you're speaking like in category notation, you write it with a cross. That's just the way it is. And what you're saying is, well, a cross is a structure. Like what are we talking about, this particular object A cross B? Well, what we're really interested in is not so much that thing in itself, but it comes equipped with some structure, so those are called first and second. So that's like the basic, I'm developing the apparatus of the thing. And the idea is that if you take, I'm tempted to write that as gamma, but I'll write it as C, which is the usual way. If you then take any m you want here, so think of this as your gamma. So this is, it's convenient to think of this as a bunch of assumptions that you're working from, but they're grouped up. So they're collected up. So m is a term of type A in gamma, and n is a term of type B in gamma. That's what this is being said. Okay, then you can form, that's this exists thing, the pair mn, which is a term of type A cross B in gamma. That's all we're saying. So this is just already, before I even say anything about equations, I'm just specifying the intro and elim rules. I'm saying, well, the product is characterized by its elimination rules. This is what makes it a negative connective. So remember, I called it a negative connective. So you say, well, you first of all say a product consists of a span, first and second, and it's a final span. So the idea is that if I have any other span, that is pair of terms from C to A and C to B respectively, then I can pair them up and get an element of that thing A cross B. So before I say anything about commuting diagrams, I'm just saying what the syntax is. So this is one way in which people like to write down the syntax of type theory or proof theory, is in this kind of notation. And I didn't anticipate that it was alien to some people. So that's why I'm going slowly here about this. Now, the beta-like rules, I'll just write beta here, and I'll write beta here, are expressed by the fact that you're saying that this path is the same as this path. In other words, if I form the pair mn and then take its second projection, it's the same as just n. That's well, I happen to do second projection first. So that's the second beta rule over there. And the first one is if I form the pair and take its first projection, that's the same as the first thing. And that's the first of the beta rules that is over here. Okay, so that's the first thing. So these cells or whatever that we're writing here, whatever we call them, these little pieces of the diagram here, I'll mark as beta. And then there's another piece of the diagram which is implicit, that's usually written by putting something like an exclamation point there. That's like the common notation. And it just means that not only does there exist such a thing, pair mn, but it's unique amongst such things. So this is what we talked about last time, and that's where this rule comes in. So I didn't quite leave myself enough room, so let's focus in on that. So what does it mean to prove that it's a unique such thing? Well, I could edit the diagram in place, but let me do it over on the side. So let us suppose, so here I had PQ, which don't line up with my M and N. So how about if my notational convention, all right, let me do them like this. Okay, so the idea is that what we have here is this thing is, so we have M, all right? And we know we have the pair PQ, because that's given by here, all right, which is in A cross B, which has the characteristic. What is the characteristic of this? Well, this guy has first, this guy has second, so that's A, that's B, and we have, these are called P, and these are called Q. So in other words, so now let's look at this scenario, like we're focusing in. In order to explain the uniqueness, what I do is I put in a balloon here, you might say. So I have a scenario where there are two things that satisfy the requirement, the beta requirements. So the two things are this pair PQ, and we know that pair PQ followed by first is Q, and pair pair PQ followed, oh, sorry, I said first, but I meant second. And if I do pair PQ followed by first, that's P. Okay, we have that. And now suppose M is a fake pair, okay, so to speak. That is, M has the characteristic that if I do M followed by first, I get P, and I get M followed by second, I get Q. Then the claim is that these are equal, and I'll write this cell, I'll mark it eta, meaning that this is equal to that. And that is what is being said here. So that's the eta expansion. So there are kind of three steps. This looks like a wordy way of saying that, which it kind of is. Okay? But this formulation of it looks more close to the notation that's used when people draw pictures. Okay? Because it says explicitly, suppose I have another M that satisfies the beta condition, then it can only be the same as PQ, at least up to this equivalence relation we're describing. So that was the thing that I was saying last time. And so, and I found that was, people weren't so familiar, so I wanted to emphasize that. So that's what I meant. So what this is beginning to tell you, so in a whole nother like tradition, this is called a product diagram. That's why this is called a product diagram. That's just, in an algebraic tradition that has some bearing on what we're doing. There's such a notion as a product, and the product has this kind of characterization. And the thing I want you to observe is that that characterization is similar to the characterization we gave to conjunction in a Heiting algebra. It's just that in the Heiting algebra, it's all very degenerate. In the Heiting algebra, the arrow in a Hasse diagram means less than or equal to. And there's no reason why. You just say, if I have A and B, it's less than or equal to A. We don't give that fact a name. We just say it is. Says A and B is less than or equal to B. We just give that fact a name. So let's move this over here. Then we say if C is less than A and C is less than B, then C is less than A and B. And this is in a Heiting algebra. And that's the universal condition in a Heiting algebra. It's the same thing. It's just that if you are looking at the judgment A is less than or equal to B, one has the point of view that there's no reason why. It just, maybe it is. I don't want to say either it is or it isn't, because I don't want to, in a constructive sense, that isn't true. But the idea is that, yeah, well, that's the best way I can say it, that there's only trivial evidence, or there is no evidence that A is less than or equal to B to consider. I don't need to worry about whether this path is equal to that path, because all I care about is that I can get from here to here. That's it, okay? I can get from here to here. It doesn't matter how. You just do it, okay? That's what a preorder is. And so, but with a category, you do the exact same thing in the sense that you characterize it by this is the face, this is the case, and this is in some way the best one amongst the ones that behave like that, where best means now it's the greatest of the lower bound. So this is a lower bound, this is a lower bound, this is a lower bound for both A and B, this is the greatest of the lower bound. So that mode of thought is very important with what we'll do next with the disjunction, with the positives. That's why I wanted to broach this. Okay, so I hope that clarified what I was doing. So it's just three notational conventions, and it's showing, however, that ideas that arose independently converged on the same thing. So one understands by that there's some tight connection between them. Okay, so that's the idea. Okay, so that's all. So there was nothing profound going on there, except that I feel that it's important that you understand the connections between these things, and also as things get more complicated, it's not always obvious exactly what the right particular unicity principle should be. So what I want to point out, that's what I want to point out, the unicity principles are associated with the universality. Like the eta that comes up here is associated with the characterization as the best amongst the final span, the best amongst spans, okay, in a certain way of saying. That's where the eta rule comes in. It's to do with the universality, the universal conditions. The beta rules come in just on the fact that the paths commute, the diagram commutes, so that the paths have an equality. So that's the sort of raw equality aspect of this, and this is the kind of type-based reasoning. If you give me any other thing of this type, then I can relate it to this thing of that type, and you see that there's a kind of an analogy there. Okay, so that's what I wanted to do, yeah.
Is there another diagram you can make to show that the object of the product is unique? Like that if there was another object with first and second maps to those things, then you could...
I'm not quite certain I understood the question.
So you showed that like the P comma Q arrow is unique, but could you show that the A cross B object is unique?
The A cross B. Oh, yeah. Oh, okay. So what? Okay. So yeah. So what Arbab is getting at is the following thing. Let me amplify it. I'll take the opportunity to amplify his question. Let me ask it. Let me pretend he asked a slightly different question. So remember, we had this discussion about partial orders versus pre-orders. So if you characterize the meat in this way. Suppose I have the meat A and B, which is characterized this way, and suppose I have another meat, let's call it meat prime, I don't know, of A and B, which is also has the same property. Then you can show as an exercise that this is less than this, and this is bigger than this, that they are interchangeable in the sense that each is less than the other. So in a Heyting algebra, it's typical to say if two things if each is less than the other, we will demand that they be equal. So in a Heyting algebra, in the usual formulation, that implies that A meet B is A and A meet prime B, and so there's really only one greatest lower bound. And it's equality. Okay, so this is what is put in here. That's the typical thing. Like I said, I kind of waved my hands a little bit because for reasons that I'm now going to explain, maybe that's not the best way to do things. You know, sometimes people just say a Heyting algebra is a pre-order, and then you have to worry about it. So what does it mean to worry about it? Well, this statement can be summarized, this less than and greater than thing. It's not so typical in the notation, but we can say they're isomorphic. And just define that to mean this is less than this and this is less than that. Okay, they're isomorphic. So you can show that if you gave me, I don't want to draw the diagram, but if you gave me another thing, A meet prime B, then it will end up being, you can check as a homework exercise, that's a good homework exercise, that they're unique. So the same happens over here. If I have one product, A cross B, that satisfies the universal condition, and I write down another product, let's call it cross prime B, that satisfies the same universal, I won't write it out, but satisfies the same universal condition except make that B prime, then you will be able to show that they are isomorphic, where the definition of isomorphic means, and now this is an interesting thing because it broaches the subject that we're studying this semester, so that means that there is some kind of a mapping between A, B, and A cross B. For lack of imagination, let me call that F. And there's another mapping G that goes backward. And so that's sort of like saying less than and greater than. And moreover, we end up saying that if we do F after G, then that's the identity, and G after F is the identity. Okay, so that's the condition that you get over here. So in that sense, the product is unique up to isomorphism. So usually that's where people stop. But what I want to do is draw an analogy, which is that this is an example of what is called a univalence principle, the univalence axiom in play. When you say that isomorphic things are equal, that is when you say in this context that two objects in a pre-order satisfying this condition are in fact equal, that is each less than the other, they're equal. When you say when a pre-order is a partial order, you're applying a principle called univalence. And the same is true here. The question is, does this mean, question mark, that A cross B is equal to A cross B prime? Well, the problem with saying that is, what do you mean by equality of objects? These are called the objects in the category, and these are the maps. So what do you mean by equality of objects? That's a sticky question, okay? Exactly because the objects are structured. If you think of these as some kind of sets or types or some kind of mathematical structure, they come equipped with maps, and because they are structured, the notion of equality should somehow reflect that internal structure, that these are classifiers of things. And so what does it mean for two classifiers to be equal? Well, typically what people do is they just say, you know, we identify things up to isomorphism, things like that. Okay, they make as an informal convention or a formal or informal convention. But in the presence of univalence, as we will see a little bit later, we'll be able to have a development of category theory inside of type theory in such a way that, analogous to the notion of a partial order, we are able to say that these are equal. And the importance of saying that they're equal is that equality has a special status in the world, which is that equality is that which everything else respects. There's no requirement that anything I write down respect isomorphism. Isomorphism is, so to say, my notion. When I'm using category theory, I say, well, when I have two maps like that, I'll call them isomorphic. But absent some other suppositions, there's no reason to think that things respect that. But if you say those things are equal, then you have no choice. Anything that you do with an A cross B must also be doable with an A prime cross B, exactly A cross prime B is what I meant, exactly because they're equal. So there's a difference between, like a conceptual difference between stipulating that they be equal from observing that they're isomorphic. And the univalence axiom, again, will put these two on the same footing. Okay? So in the last lecture, I stumbled over this because as soon as I wrote down A cross B, I was misleading you. Okay? Because I really should have said Z, I don't know, pick something out of the air that doesn't look familiar. I'll say Z is a product if Z has a map here, Z has a map here, and it satisfies this universal condition. And when Z is such a thing, we tend to write it as A cross B. You got to be careful about that, okay? But when I did that, what I was doing is, it's sort of implying by this notation that I'm computing the Z as a function of A and B. But then I must admit, what does it mean for two A's to be equal, and what does it mean for two B's to be equal, so that it makes sense to treat cross as a function? Okay? And so the standard notation is, unless, you know, people get used to it and are, you know, don't make mistakes, but it is a little deceptive, right? But it would have been hopelessly abstract if, you know, it feels like it's kind of alien if I say to you, well, Z is a product of A and B if, but that's really the right thing to say. And then you say, and I usually write, for a particular choice of Z, I will write it A cross B. So this is whole business about choosing things and stuff, and what it means to be equal as classifiers and so on, is like, that's at the heart of what we're doing this semester. So that's another reason, so thanks for the question, that's another reason why I'm broaching the subjects early, because now even before we get to dependent types, already lots of these issues that are central in type theory, and homotopy type theory in particular, that a lot of those issues which are central will now, you know, are appearing already at such a, even at the Heyting algebra level, they already appeared. Okay, but people usually don't make a big deal about them because in isolation maybe they're not a big deal. But when seen as part of a larger thing, they kind of are a big deal. So, so that's why I'm drawing out that structure now in ways that previously you might find people wouldn't dwell on. Okay, so that's my reason for doing this. Okay, so now the next thing. So the next thing is...
I have a quick question about equivalence.
A question, yeah, sorry.
So it seems like the beta rules want our equivalence to be coarse, right? We want things to be equal that may be syntactically different.
Yes.
And the eta principles want them to be fine because we want things that are equivalent to have certain properties.
Yeah, that's right.
So are we defining equivalence as the finest thing that satisfies beta, and we'll show that it satisfies the eta rules?
Yeah, so the whole, okay, so now the inside game of my whole discussion, which you're exposing, is this. What is the definition of this notion of equivalence? Okay, so what I'm trying to do first of all is propose some things that are understood, and then I want to put them in a larger setting so that I can properly answer your question. So it's entirely intentional to get you to irritate you to think about these things, because that's what I'm trying to do. Okay, so what I'm going to end up saying, just to foreshadow it kind of in anticipation of your question, I'm not going to be able to prove this to you, but I feel that there is something somewhat different about the nature of this equality than the nature of these equalities, that the beta equalities are of a somewhat different character than the eta equalities. And this will be more apparent when we deal with sums. So let's deal with the disjunction. So when we look at the rules for the beta rules for disjunction are okay. But if I now ask you, so we're in the eta column now, because the beta is like presents no issues. It's the eta that presents the issues. So when we're in the eta column, I've written down some rules for truth and conjunction and implication. So now I want to resume over here. I'm in the eta column and I'm looking at disjunction. Let's do that first, okay? So I want to say something about disjunction that expresses some kind of unicity principle. So you can feel my way of saying it is awkward. It's intentional, because if all you had in your hand was proof theory, there's not so obvious what it is you're supposed to say. Okay, so you start casting around for ideas. So the unicity principle sort of is trying to express the idea that every proof of a certain sort, that a certain type or a certain proposition, can be put into some kind of standard form. But if you tried to write down, like, let me try to do this with you as if you never heard of any of this before, and we'll just try to invent it from scratch, right? Because it'll be awkward. So the first thing you might do, you're just casting around for ideas. So you're sitting in your office and you say, okay, suppose I have a proof of A or B. Let's not worry right now about the variables. What might I say about it to express its uniqueness? Well, you say, all right, I have this. So I might like to say that M is in left of P, and now you're worried because the format is not really the same as what I said before. M is in right of Q. Okay. But it's a little bit of a worrisome because, inference rules are not like some random thing you write down with a horizontal line. So this is like problematic, right? How am I supposed to express this? Clearly, I cannot write two rules, like one rule with this and one rule with that. That makes no sense whatsoever, because obviously this needn't be an in left. It could have been an in right. And it needn't be an in right because it could have been an in left. So I'm kind of screwed here, right? And I don't know what to do. Okay, so let's imagine we were Gensen a long time ago, and it's the first time we ever thought of this. That's what I'm trying to do with you. Okay, so I don't know what to do. So that's like a non-starter. I get in trouble. But now you think to yourself, well, there is a kind of a way here, and let me do it in the backward order. So let me have a point of inspiration that might appeal to you. I have no reason to believe that Gensen thought of this, but I'll just do it. So here's a point of inspiration, which you might have seen somewhere, is the notion of the Shannon expansion. This is the core idea of binary decision diagrams, if you know about this. Okay, if you know about BDDs. So what is it? It's an aside at the moment, but the inspiration is, you think you're casting around, you don't know what to do. The Shannon expansion. So here's what I'm trying to get you to think about. If you look at the special case of the proposition true or true. Okay, that's a perfectly good proposition. All right, I need to give that a name, and there's no logical name that I know for this thing, so I'll just write it as 2. Okay, so this is the type of bits, because what are the canonical forms, the introductory forms of this type? In left of the null tuple or in right of the null tuple. Let's call those true and false. Okay, so those are the bits. Okay, so we can say in left of the null tuple is one element, that'll be true. In right of the null tuple, that'll be false. Okay, notice what I'm doing to you. I'm doing something else to you in case you didn't notice. I'm drawing some distinction between propositions and Booleans. okay? And I'm doing that on purpose, okay? These are the Booleans. These are some data that inhabit this type, and they themselves are not propositions, okay? They're elements of the type 2. There's something fishy in a way, because the standard story you learned in school was there are only 2 propositions, they're true and false. So what am I doing here? Well, we'll get to that. Okay, so let me just continue with you. We'll write it like that. So what would be the elim form? Well, the elim form is, if you look at what case analysis is, case M, since there's no interesting data associated with it, there's really just 2 cases, P and Q. I don't need the x.p and the y.q because I already know it's the null tuple. And I know that because I have the uniqueness principle that whatever it is, it's the null tuple. So I could write it like that, or I could write that as, which really is the same thing as if M, then P else Q. And that is called a BDD, a binary decision diagram, because I'm making a decision on a binary data, M, and then transforming that into one of 2 things. Well, it's a BDD in the special case that this is also of type 2. That's why they're called binary decision diagrams, because everything is a decision diagram. So now what is the Shannon expansion? The Shannon expansion is the following thing. It says, if I have a term let's look at a big fat BDD, and let's pick a subterm of that BDD. Okay, that's what I'm doing here. Look at M for XP. Pick a spot. Personally, I like to call it a pivot. I don't know whether everyone calls that a pivot, okay? But what I'm going to do is I'm going to pivot on M. What does it mean to pivot on M? I'm going to say this is equivalent to if M, then substitute true for x in P, and otherwise substitute false for x in P. Q, sorry, Q. This is called the Shannon expansion, SE. I'll just write it SE. This is called the Shannon expansion.
Both P.
Oh, did I screw it up?
It's P in both branches.
Oh, P over here. Yeah, I said P, and then I said, oh, no, Q. But what's Q? No, I meant P after all. I was right the first time. Sorry. Okay, sorry. Okay, so that's called the Shannon expansion. Okay, so just for the sake of recording it, we put a big question mark there. That doesn't make much sense. Okay, you don't get to write whatever random stuff you want above and below the line. Okay, so now, that's called the Shannon expansion. So what is it doing? It's expressing a standardization property. It's saying, well, I've got some arbitrary subterm M. Maybe it's like what's convenient is, think of the special case that's just a variable. This is what they really do with BDDs. So that's a special case of this is, if I have a variable, let's write it P, and I have to somehow emphasize that I'm picking X. So there's an X in there, so I have to write like that. Then what you do is you turn that into case analysis, branch on X, and then propagate true for X in P, and otherwise false for X in P. That's a special case. It's a special case where M is itself a variable, okay? And the whole engineering edifice of BDDs is really the heart of it. Is the whole idea of a BDD is this Shannon expansion. That's what it is. So you write it like that. So you may have seen that before. So what it's doing is it's expressing the idea that X can be none other than true or false, which is kind of what I'm trying to do here. I'm trying to express that M can be none other than in left or in right. That's a generalized form. Okay? So how do I do it? Well, now you can kind of guess. You can kind of see what it is I might want to do, but it's going to look a little different from the unicity principles over here. So it has like a different shape. And the reason is that these are all positive or negative types, all right? These are I don't know where to put the notation, but to remind you, those are all negative types. This is a positive type. And this is the characteristic of positive types is what I'm about to show you. So what I'm going to want to do under suitable conditions, let me just double check how I wrote it out here to make sure I try to be self-consistent as much as I can. That's asking a lot, but I can do this. So I wrote it out like this, yes. Okay, so blah, blah, blah. Give me a moment. Okay, so what I want to do is I want to look at a term with a free variable. So the idea is, what I'm going to say is this, all right? I want to say, if I have some term p, then p is equal, well, it's actually going to be, let's do it exactly like I have here. So if I want to look at m for xp, there are different forms of doing this, but m for xp is the same as you case analyze on m, and you have, in the in left case, what do? You plug in left of whatever it is, x. Oh, let's not call it x because that'll look a little confusing. So let's call this y for x, because I called that x, or else if you want to be consistent in a different way, let me write that z. So then we'll go back to what I did before. Sorry, excuse me for that. So this, I was calling that x before, so let's try to be consistent. In left of x for z, and y in right of y for z. Sorry, in p, excuse me, in p over here, under suitable assumptions. And what are the suitable assumptions? I have a proof of a disjunction, and p is a proof of something else. So all this is in C. And actually, those are the only assumptions I need, I'm pretty sure. So that this together with that tells me that this is of type C, and this equation will be of type C, and I'm pretty sure if I didn't screw it up, this should have the same type. Okay, like that. So this is, again, the kind of Shannon expansion. Okay, the Shannon, this is the, maybe we could call this the generalized Shannon expansion if you want, because Shannon's expansion worked for bits. It only worked for the proposition true or true. So I want something that works more generally, so this is the generalized form of it. Of course, it's a minor generalization, but anyway, it is a generalization. So this is the generalization. So this is how, this didn't work, okay? This doesn't make any sense, although there's some intuition going on there. And the way you actually get this thing to make sense is you say the Iter rule for disjunction would be that. Okay? So that's one way to write this. Yes?
Bob, you might want to put gamma in below.
And then there should be some gamma around, yeah. Okay, so this should be in gamma because I was trying to synthetically, I was trying to synthesize the rule. Okay, so that's in gamma. No? Did I put it in the wrong place or what did I do?
That's right.
What did I do?
It's fine, but also the x free in p should be.
This should have been z after all. Okay, so let's fix that. Okay, and then something about x is free and what?
No, that, what you just did.
What I just did, it fixes it. Okay, sorry about that. I changed my variable names midstream. That's always a mistake. Okay, so, okay, yeah, that's what I meant to do. Okay, yeah. Okay, so that is the correct rule. Let's look at a special case of this, which is worthwhile. So here's a special case. And the special case is what happens when p is just z. So like in the BDD world, they tend to emphasize what happens when m is just x, or maybe I should have called that z after all, if I want to be. So if you're doing notes, it would have been better if I called that x. So z, because then it matches up with that. So let's say I did. Okay, so they focus on the case of pivoting on a variable. I want to focus here on another case, which is the expression itself is a variable, so that we're pivoting on all of m. Okay, so let's work out what that special case is. It says that if we have m is equal to case m x dot in left of x, because I'm plugging that in for z, and that is z, so I get x dot in left of x and y dot in right of y. That comes pretty close to what we were trying to write here, okay? We obviously thought that was broken, but the non-broken way to say what we were doing is to say, oh, right, m is a case analysis between these two things. You see what I'm doing? See, what I'm doing is I'm taking the thing apart and then putting it back together out of its exact own constituents. Because once I do this case analysis, I know that M is an in left if I'm over here. And it's in left of, I don't know, God knows what, but it's X. So let's just reconstruct it. And the point is that unlike, sorry to bring up dirty things like memory allocation and stuff like that, but in low-level programming languages, you might have to worry whether a copy of something is the same as something. Okay? But here I don't have to worry about that because I'm dealing with a civilized functional programming language. So if I take M and take it apart and put it back together, I get the same thing. It's just like saying, you know, it's kind of dumb to ask, you know, if I add 2 plus 2 and I add 3 plus 1 and they're both 4, and then you ask, well, is it the same 4 or a different 4? Okay, well, in some situations that can actually be a meaningful question because of the representations. You're dealing with the low-level representations of things on like hardware, and then you might worry about something like that. But anyway, here we're not. We're abstracting from that. So we're able to say something like this. So although it doesn't quite look like it at first glance, it's trying to say the same things as an EDA rule is saying. Okay? That is, it's trying to say that it's trying to get at this idea of take it apart and put it back together. Okay? Take it apart and put it back together. Okay? And here, well, you just put it back together because there's nothing to take apart. So that's what's being said here. And this says take it apart and then put it back together. Well, this instance of it says take it apart and put it back together. Okay? So that's one of the like basic principles that's here. Okay, so now you might reasonably ask, if you had no like other experience, and you would, even if you did, you might reasonably ask, is that the only rule I need or what? See, because there's always this worry when you just start writing down stuff and you just say, okay, my definition of this relation is what I'm writing down, but, I leave that alone. But you should sort of ask yourself, what makes that the right thing? You know, like, why is that the right thing to say here? Well, maybe there's no really definitive answer to that question of what is the right thing to say here, but we can at least provide some insight by saying, oh, these other guys who I never thought I would talk to in a million years have come up with the exact same notion in a different notation that says the exact same thing I just said. So anyway, we're in the same boat. Okay? All right, so that's what I'm going to do next. Yes?
Just a question about what you had before there. In what sense is the special case not as general as the rule above? Because I think I could derive the rule above from the special case.
No, you can't. You need.
Why not?
You need. Well, because of where you're going to get the p. You need one more rule, which is actually I was holding in abeyance for the time being. Okay, I will get back there. So it turns out you can derive the general case from this special case and one other thing. So I'm going to leave that as an exercise. Ha. Okay, which is. You just need one other principle, general principle, that lets you derive it. So I'll give you an example. Here's an analogy. Let me do the analogy thing. The analogy is, the analogous thing is, I could have expressed the EDA principle for products only for variables. But it wouldn't have been enough to derive the general case until I tell you what substitution does on a pair. Because then I would get that M for XX, which is M obviously, is, by this equation, M for X, oh, I'm always using X. No, X is the right thing, yeah. M for X in the pair first second. So to derive the rule that I actually wrote that has now been erased, I would need one additional step, which is to know that this is actually first of M, second of M. And what that's telling us is we know how the substitution interacts with this pair. What is the definition of composition? Is what is going on here. If you think of this as sort of function composition, okay, then I'm doing a kind of function composition. This is the thing with an X in it has a free variable. It has a domain, which is x, is ranging over the domain. And then I'm plugging in m for x. So I'm composing this map with this map. And you need to know how do they interact. So this equation, knowing how they interact, together with this axiom, you can derive the general rule that I gave. Well, there's a dual thing going on here. Okay? And you should figure out what that is based on that hint. Okay? All right. So yes, you can do that. So it's not enough to do just that one thing. Okay, so I was going to now write out in diagrammatic notation. Let me erase what I wrote here.
Do the thing in the other case, you'd need like a slightly different.
Say it again, please.
Wouldn't you need a different type of substitution?
Well, there's another, yes, I mean, yes, but how much of a hint do I want to give? I mean, I can just give the answer. Okay? But something has to be figured out that is the dual of what I just said. So I thought that was maybe enough of a hint. Okay. And if it isn't, I'll help you. But anyway, let me not just do it. Okay. So let's write this now in diagrammatic notation. Because I was saying before, what makes these equations canonical? Well, the fact that these other guys think they're canonical. That's basically all I can answer for you, right? And then it turns out there's yet another set of guys who thinks that they're canonical. So anyway, we're all in the same boat. So this is the boat we're in. So the boat we're in is this notion of a coproduct, which, or a sum is sometimes called, but a coproduct more typical, which is written like this. Okay, so a coproduct is what is called a cospan. This is the terminology or the notation that people use. So again, that same issue about the misleadingness of writing plus A plus B and A plus prime B and stuff. If I really wanted to be like turn the screws and be absolutely rigorous, I would say Z is a coproduct if it has these two maps, but I'll write it like this. That's more common to do this. So the coproduct, a coproduct, is given by two maps. It's called a cospan, because if this is called a span, this goes the other direction. This goes out, right? These ones go in, so it's called a cospan. So you give me a cospan, and it's an initial cospan. That is, it's the best one amongst things that do the following thing. If you give me, I guess I was calling this P and Q. You give me P, and you give me Q, which goes to C here. So you notice that things are kind of dualized, okay? Then there's a map, and then it's more usual to, I'll use curly braces, to write this as curly braces PQ, which is going to be stipulated to be unique. So you can think of that curly braces PQ, that's sort of analogous to case, well, you have to have you're going to have a variable, case some argument, so case blank, it's really kind of like analogous to x.p, y.q. So I'll just say analogous to, okay, that's what I mean. Okay, because the x in this, yeah, that's the idea. The x in, so P has a free variable of type A and computes a C. Q has a free variable of type B and computes a C. So that's what's going on here. So this map here represents that scenario. And the case analysis with a blank here has a free variable of type A plus B that computes a C. So that's what you're supposed to think of. This is the usual. A lot of times people write square brackets here, but I've been using square brackets so much for other things that it would be better if I don't do that. But more commonly, you'll see square brackets for that. Okay. All right, so I'll write it as curly brackets. Okay, so we have curly brackets PQ. Sometimes that's called a co-pair, just because, I don't know, it's cute or something. If this is a span and that's a cospan and this is a pair, then that's a co-pair. Okay, so that's the cute way. So what does it mean for the diagram to commute? Well, the beta rules are here. So those are the beta rules. If I case analyze on an in left of something, then I get back the in left of something, I get back P with the dependency on the something. Because you see, I'm doing in left of x is some variable A, and feeding it to the case analysis, and I'm saying if I do that, then I will do what P does with the same thing that got fed into the in left. Okay? So that's a way of thinking about it. Okay? I hope that's reasonably clear. So what we're saying is, here if you write it out, it's sort of saying, you could write it in this, it's saying case of in left of blank, x dot p, y dot q. One of the beta rules is that, one of the beta rules, which I've since erased, is that this is blank for x, p. Okay, when I wrote it before, I wrote m and I wrote m for xp, but here I'm trying to like leave it as a whole, which comes in from the domain of the map. So that's the way of saying it. So that's this side, and the right side says a similar thing, right? If we have this, then this is blank for xq. Okay, so that's the other beta cell that is going on there. Okay, so we have that. All right, so that's the first thing. Now the second thing, which will lead to another formulation, so we'll see this. So now let's blow this up. I'm going to do this one in place. Okay, so now let's blow up that exclamation point. The exclamation point says, well, we already know by the definition of a coproduct that we've got a copair, PQ, and we're going to claim it's unique. So if you give me any other M here, okay, that has the same behavior. If I feed in left to M, it's the same as P, and if I feed in right to M, it's the same as Q, all right, then M is the case PQ, and that's the eta, which goes right there. Okay, so that arises by doing the following thing. We can say it, I hope I can get this right. So this says, if for x in A, in left of x for z and p is, oh, my p's and q's and stuff are all messed up. Oh, I did that again. Oh well. What I called p and q should have been m and n and p. So how about if I do that? Okay. Is that what I want to say here? I better not. No. I got this right. What is it that I want to say? I'm messing up my notation. What I want to do is I want to express the idea that if in left of something in M, M is doing a kind of case analysis. So in other words, so that's P over here. So I'm saying that if I do in left, I better write the rule. I better write the rule out from scratch rather than edit that rule, because if I edit that rule, I'm going to confuse everyone. Okay, so I don't want to do that. So what is this thing saying? So this is saying I have M, which has a free variable of. This is where I have a notational mismatch. So M has a free variable of type A plus B, okay, and it computes a C. That's what is being said here, okay? That's the first thing that is being said. And we know that if you give me X in A, that's what's going on here, that in left, let me not call it X. How about if I, yeah, oh geez. All right, so there's another issue about the variables. So let's call it Z. Pardon me for my variable names. Okay. If I do in left of X for Z in M, okay, and if that behaves like P in C, you see, because P goes from A to C, right? So it goes from A to C, right? So that's what P is. And if M, when given in left, behaves like P, and moreover, this should be B, and M, when behaved like this is Q, it behaves like M behaves like Q, then generically in that Z, M is none other than the case PQ. Well, using that notational convention, but let's write it out like we did with proof theory notation. Okay, Favonia will check me, but I think case Z, oh no, yes. Did I do this right? I hope I did that right. Okay, let's double check, right? So we're saying, right, we have an M which is you can think of it as a map or a function of A plus B, And when run on in left, it behaves like P, and when run on in right, it behaves like Q. Well, then it's none other than the case analysis, okay, that pivots on Z, that argument Z, and behaves like P and behaves like Q accordingly. Okay, that's what is being said here. Is this boring, Joe, or what? No, you're okay. Okay, so am I going too slowly today? Last time I went too fast. Okay, all right. So if we have the M like this, so then this equation, what I want to say, is the same as essentially expressing the same thing as that one. Okay, so that's the notion of a coproduct. So that's where these rules come from. But now here's the thing that I want to suggest, that I want to throw into your eye here. What is going on is, think about what I'm doing here. This is really an induction principle. That's the thing that I want you to see. And it's a characteristic of a coproduct or of a positive type in this way. That what happens is I say, I can characterize the behavior of M generically in Z by breaking it down and doing a case analysis on what happens on in left and what happens on in right. And if I can do that, then I know it must be this case. So it's a kind of proof by induction. So in particular, if you show that if I have M and M prime, which behave the same way on in left and behave the same way on in right, then they must be equal. Because they're both equal to a case. And they're both equal to a case, then with transitivity and symmetry, they're equal to each other. So it's an induction principle. What's happening is you're saying it's a proof by induction that is going on here. It's a degenerate induction because a case analysis is a degenerate induction. Whenever you have a finite type, the induction principle for a finite type is do all the cases. And so that's what I'm doing here. I'm doing all of the cases. So now I want to get to, how am I doing? Okay. Now I want to get to like this point about the distinction between the beta and the eta rules. So the idea that is particularly obvious in the negative case is that this idea that the beta rules seem to be kind of analytic judgments, which means which is self-evident. You can just look at them as equations and they're justified because you have a lambda applied and you plug it in. That's all there is to it. Whereas the eta-like rules seem to be more of the character of synthetic judgments, which require evidence or require proof. You see, for a beta-like principle, you just look at the two sides and it's obvious that they're equivalent. You don't need to do a proof. Here, in some way, I admit that there's a subjective element to this, but that's the best I can do, okay? Which is that I needed to actually do a case analysis. I needed to do a proof by induction in order to justify this equation, right? And somehow that makes this feel like this eta cell that is being filled in here is somehow different in flavor, possibly, from the beta cells, which just express a principle of simplification. So we're going to get to that because what's going to happen is what we're going to do when we look at ITT and when we look at homotopy type theory, the beta rules are going to correspond to what is called definitional equality. Definitional equality. That's just the established terminology for it. It's a definitional equality, which is supposed to be an analytic judgment, whereas the eta rules will more typically and more naturally be thought of as a propositional equality. Okay? And what I mean by that is it will be expressed by a type. Unfortunately, there's a word. I would like to call it typical, except that somehow it doesn't quite ring right. Okay? But it's going to be expressed by a type. There's going to be a type expressing these equations. And that is different from a definitional equality, which is judgmental. So it's sometimes called a judgmental equality, not because it is making moral statements, moral evaluations, but just because it is a judgment, okay? That is, I just say, I judge that these two things are equal. It's an analytic judgment in particular, so it's self-evident. Whereas when I say that the eta-like rules are true, they're going to be true by virtue of a proof. It's going to be a synthetic notion or a typical notion. And this is the central thing in homotopy type theory, is a distinction or the interplay between definitional and propositional equality. And that's the thing I wanted to get to today. Okay, so good. So that's what I wanted to do. Now, you might reasonably say, okay, I don't know whether I believe all this. It's a little woo-woo because what does this all mean? Then I can only say to you, I will play out more consequences of this as we go along, and I hope it will become more apparent. But I'm trying to broach the subject, okay, that I think is very important. So what I'm going to do next time is, so next I'm going to look at a system called Gödel's T, which can be thought of as, at least my version of it will be, this intuitionistic propositional logic plus some data. And I'll have what is called a natural numbers object. That's the terminology that is used here with the natural numbers object. And so what we're going to do is we're going to now be developing this propositions as types analogy. So we have propositions, and if you look at the type, the characterization categorically, that's a final object. You look at conjunction, that's characterized categorically as a product. If you look at the contradictory proposition, that's an initial object in a category. If you look at the disjunction proposition, that is a co-product. That's what we've been discussing. I haven't developed 100% all the correspondence, but I hope you can feel what's going on there. And then I have implication, which is an exponential on the categorical side. So on this side, this is sort of types, we could say. It's just a matter of, the part of the message here is that what is a proposition, what is a type is a matter of your attitude toward it. There's no like real fundamental difference. Okay, so far we have a complete correspondence, but what we're going to do is we're going to introduce something that feels more like data. Okay, and over here eventually we're going to introduce something that feels more like a proposition. This is this propositional equality, and doesn't feel so much more like data until you realize that if you think of it as data, it corresponds to the idea of paths in a space. Let me write Blackboard bold for that end so they don't look confusing. So these are going to turn out to be exactly the same thing. That's where we're going to go. But a thing I'm trying to say is that when you say type, you sort of feel like it's data. When you say prop, you sort of feel like we're talking about proofs. But really, it's just a matter of how you feel, because it's you can go back and forth between them. So the justification for the props as types principle is that an independent theory of data corresponds to an independently given theory of equivalence of proofs. So we kind of feel that therefore it's legitimate to say those are the same. They're not just like, oh, a cute thing, they happen to look similar. You could maybe argue from this point of view that they really are the same. But then as soon as you start populating this a little bit further, you start wondering, well, what goes in which column? And I'm just trying to say here in closing that, well, there's only one column really. It's just like how you cock your head. And so we won't really worry about which things fit in which column, because there is no column for them to fit in. Props and types are the same thing, and we'll just we'll tend to have a different psychological attitude towards some than others. That's all. Okay? So that's part of the whole beauty of type theory, is a complete integration like that. It's not like you have data and programs that manipulate them over here, and then you have logic and proofs that say something about the programs. The math is the data. The math is the code. Okay? That's the project. Like, that's the overall idea. And that's, you know, that's quite beautiful. If it works, it's quite beautiful. And so we've been trying for decades to make it all work, and it does work to a remarkable extent. So that's the, so let me finish off with that for today. So next time I'll talk about the natural numbers object. That has a universal characterization, which is very important for you to understand. And that will then allow me to have a discussion of families of types. So I will then talk about type families and relations, and we'll be talking about dependent types at that point. Okay, thanks.